Okay. Mm, So, welcome everybody to the August meeting of Tucson Amateur Astronomy's Fundamentals Group. I'm Connor Justice. I think most of you already know me from looking at the attendees for tonight. Uh, for those who may be watching this on YouTube later, this meeting typically goes with two portions. We have a basic introductory presentation on either an astronomer or a constellation. This month, I'm presenting on the constellation Draco. And then after that, Doug Smith will be giving our main talk, which is about using the stars to navigate or stellar navigation in general. Doug, correct me if you have anything you
Close
want to
enough.
add. Close enough there? Okay. Um, as you're for those on the meeting, just go. I do have the chat open in front of me, so I am paying attention to that. If you have type questions, alternatively, you can just unmute and feel free to ask the questions whenever you want. I'm typically good with that. Either way, I'll leave it up to you. And then kicking this off here. So as I mentioned, we're going to be starting out here with the constellation Draco. I try to keep constellations to ones that we can go look at this time at the time of year in which I present them. Which being monsoon season, unfortunately means you're probably not going to see it anyway because of clouds, but uh, we can hope. So Draco is the sixth largest constellation in the night sky, following Virgo, Hydra, Ursa Major, um, Pegasus, and Pegasus, I think, are four of the larger ones that come off the top of my head. It is also one of the original 48 Greek constellations that was cataloged by Ptolemy in the 7th century, which, like many of Ptolemy's constellations, they do essentially have some origin in Mesopotamian lore. And that Egyptian culture thing was actually a mistypo. I should have removed that. But it does have some parallels with Egyptian culture just because of the age, although it wasn't actually, um, the serpent itself wasn't associated with Egyptian culture, as we'll briefly talk about here at the bottom. Uh, this is one of several constellations that is circumpolar in the northern hemisphere. So generally, if you are 32 degrees north latitude or higher, you'll see this constellation year round. Being here in Tucson, this is one of those that's right on the cuff of it. So we kind of get most like half of a third of the year. It's kind of down in the muck of Phoenix. But nonetheless, it's best visible for us here in Tucson from June through November before it starts getting back down into the mucky areas of the night sky. Uh, that's a mistypo. That's not, Thuban is also not the brightest star in the constellation, but perhaps its most well-known star, I should say, Thuban, was the polar North Star from approximately 4000 BCE to about 1800 BCE, which means it was mostly the North Star for the majority of ancient Egyptian mythology, which is where its prominence for their culture comes in. And all of the pyramids are generally aligned to some orientation of where Thuban was in the night sky during that time. Because of the Earth's wobble in its orbit, called precession, it will eventually return to the North Star in the 21,000s. The constellation also lies firmly off of the galactic plane, so there's not really a lot of interesting nebulae, uh, emission nebulae, or dark nebulae to go look at, or generally even any open clusters. It's surprisingly devoid of notable open clusters, but it does have quite a few galaxies and a couple of galaxy clusters. Most of them are quote unquote bright for galaxies, being around the 12th magnitude or brighter. So I, those are typically well within the range of where you can, with modest optics or magnification, you can generally see something of the galaxy. Below 12th magnitude, it typically kind of gets to be a bore of aperture and the expensive gear. It also does have a very notable planetary nebula, which we'll also talk about here later. So this is a rough star chart. Well, not a rough, a star chart of the constellation. As you can see, it's kind of sitting here between underneath Hercules, which plays a bit of a portion in the constellation's overall lore itself. And it's nestled firmly between Ursa Major and Ursa Minor, which gives it a little bit of an easy landmark for those looking to go find it. And Cygnus. We got Cygnus over here off onto the left-hand side. The primary mythology that this comes from, or at least that we have notable records of at least, is, well, of course, with the Greeks and our good friend Hercules and his, or Heracles. And the it is the constellation itself is attributed to the quote unquote dragon serpent Ladon, who was the guardian beast of the golden apples of Hesperides. Uh, to the Greeks, the term dragon was, or at least the way that it's interpreted now, was just the word that they used to denote a large constricting snake, which differs a lot from the classical interpretation many people now have of dragons from medieval lore and fiction, which is the beast with the wings, and that breathes fire. The Greeks had a very much different take of dragons, which more closely resembles that of what Eastern dragons look like, which is basically just a long, wide, long serpents. The dragon itself is attributed to multiple potential parentages in Greek lore, potentially being the offspring of Ceto, Typhon, Ishinda, or Gaia, depending on the source. Gaia being one of the Titans, Typhon and is want to remember the one of the weird offsprings of Hera and another set of creatures, and I think was also the offspring of the parent of Medusa. But unfortunately for this dragon being associated with Hercules, he was of course killed by Hercules as his 11th later to King Eurystheus. Nothing notable there. He just basically walked in, fought the dragon, and walked off with the apples. No real contest there. One of probably the simpler labors for Hercules to have done. And nothing really much notable there, unfortunately, about this dragon, which I could find reasonably quickly. Moving on to notable stars in the system, which is how I normally do this. We have a brief list. There's a couple of stars that are very much brighter than magnitude 3. There's Rostopon, Elfhanan, and Athenabine, which are the 3 brightest stars of the constellation, respectively, as we can see on this list. And then, as I pointed out here, we have Thuban that's kind of in this middle range of 3.6. Despite being not the brightest star of the constellation, and is actually probably one of the dimmer stars, it does bear the Bayer designation of being Alpha Draconis. Normally in the Bayer designation system, the Alpha star is the brightest star in the night sky, or more often than not, at least the second brightest star in that particular constellation. So Thuban is very much a deviation from that list, being like the 6th brightest star in the constellation overall. It's not quite clear why Bayer decided to give it the Alpha designation, probably because of the association. I don't know if he knew about the association of the star with ancient Egyptian culture at this point, because this was probably I think that was one of the more late 20th century findings that we found about this star. So it is kind of interesting that he did go with the Alpha designation. The star itself is a spectroscopic binary, meaning that its binary component we've only been able to detect due to spectrographic instruments. And the primary component consists of an A03, which is a designation for a very bright blue giant star. It has a very visual magnitude of about 3.65, which we saw earlier. And its mass is solidly about both 3 and 5 times that of the sun for mass and radius, respectively, and a luminosity of about 2,400 sols, which I found a bit odd for a blue giant to be that low of a luminosity. Normally, I would associate blue giants being in the later portion of space to be at least somewhat vibrant or much more intense because of their age, with stars normally getting brighter as they age. Its distance itself is a very relatively close 303 light years. as we can see here. It is also not anywhere close to being near the heart of the snake tube, with it being closer to the end of the tail. And we have on our right the Hertzsprung-Russell diagram showing where our star falls. So it is almost, but not quite, into the B classification of stars. So it is very much going to be one of those stars that dies young, being already in the giant phase of its life cycle. Moving on, we go to Eltanin, which is the brightest star in the night sky, but oddly also bearing the gamma prefix for Gamma Draconis. And the name Eltanin derives from the Greek word great serpent, which is fitting for this star's position as being in the actual head portion of the asterism of Draco itself. It is it is also a binary star system, with the primary star being a K53, which is a red giant star, orangish red giant star, mostly closer to red though. It has a visual magnitude of 2.2, which is definitely on the bright side of stars that we can see in the night sky. Yeah, but being roughly 2.14 sols in mass and 52 sols in radius, which is for a giant. Interestingly enough, for if you on Thuban, which was like only like 5 times the size of the sun for being a blue giant, this is very much larger than that. So it's an interesting dichotomy of them both being giant phase stars, but having vastly different radiuses for that. The luminosity of Eltanin is of that 6,000 suns, and it is noticeably closer at 154 light years. This star is often used by professional astronomers as both a calibration and baseline star, because it has generally been known to have a very stable spectrographic signature over time. And so when launching new instruments, they will often use gamma, Eltanin, and Vega as a way to compare and calibrate the integers and make sure that they are producing good signals. Interesting facts about this is that it will also be the star itself is approaching our solar system. It'll be within 28 light years of Sol in about 1.5 million years. So we got a couple ice ages and a couple apocalypses left to go before we get there. But by the time it does get to its closest approach, it will be almost as bright in the night sky as Sirius is today. It has, and as to give you an idea of how close it's moving, it is approaching us at a paceful velocity of 28 kilometers per second. So that's the negative radial velocity indicates it is moving close to us rather than away from us. As I did mention, the star is very much located in the head of the constellation's asterism itself, being one of the two stars that form essentially the eyes of the dragon, you could say. And on the right, the Hertzsprung-Russell diagram. So we do see it is off here onto this right-hand side of the giant asterism, well off of the main sequence branch. And the last star we'll move on, which one I don't have any good statistics on, but it was a bit of an interesting thing just to call out, and also because I like the Greek letter Omicron because it sounds menacing, is another binary star system with two components, and one of them is a variable star system as well, a variable star as well. This interesting in that it is considered the North Pole star of the planet Mercury. So if you ever find yourself on the planet Mercury and look up, you'll see Omicron Draconis right there in the middle where we normally see Polaris. Although it is a fainter star than Polaris overall. It has a visual magnitude. The primary component of this double star system has a visual magnitude of about 4.65. But other than that, it's roughly equivalent in terms of mass and radius of this, well, not of mass being only about 1.35. So it does seem like it has been a late evolution star that shed a lot of its mass and then is entered into late as it transitioned into the giant phase, because yellow giants themselves are not typically very common compared to red giants and blue giants, at least in terms of stars that we've talked about over time with these presentations themselves. It is also somewhat close overall, being at a distance of about 107 light years. Moving on to some notable deep sky objects to go look at. As pulling this back up again, there is a smattering of galaxies, although this chart doesn't actually list any notable planetary nebulas, which we will talk about one in particular. But as you can see, almost all the galaxies which are on this right-hand side column are brighter than magnitude 12. So there's definitely, for those who like hunting galaxies or small targets, Draco does present a wide number of opportunities for this. Of the notable galaxies that we'll talk about, we'll start with Messier 102. This is colloquially named the Spindle Galaxy. It is an edge-on spiral or lenticular galaxy. Since spiral and lenticular is very much a visual designation and the galaxy is edge-on, it's hard to say definitively which one it actually is just because of the ambiguous nature of cataloging lenticular galaxies in particular. This galaxy is brighter on the brighter side for visible for galaxies that we can see, coming in at a very close visual magnitude of about 9.9. It is, although a little bit small, coming in about 4.5 arc minutes in length along the long side, being a little bit closer to 80 million light years away and a diameter of about 76,000 light years. So it is definitely a galaxy that is on the smaller side compared to the Milky Way. However, despite this actually being in the Messier catalog, it is actually not certain if this galaxy is the galaxy that Messier originally cataloged. Messier 102 was originally forwarded to Charles Messier for his catalog by another French astronomer called Renaud Michain. But then there was some confusion between the two, and Michain refuted his claim, denied his claim to cataloging this object, and so we actually don't know what galaxy or object was the original target that was observed by Messier or cataloged by Messier into his list here, which is one of those interesting. So there are actually a couple of different candidates that have been proposed for this object. The most widely accepted one now is the one I show before you, which is cataloged as a Messier 6 M102. For those who are very much on the visual aspect of astronomy, this is a simulation of what the galaxy would look like if you were on an 8-inch spectroscopy using a 10-millimeter eyepiece with basically an entry-level eyepiece field of view. So it is, would definitely fit the category of a fuzzy, bright blob when you would go look at it visually, but distinct. It is a very bright core. The one planetary nebula that we'll talk about here is arguably one of the more well-known planetary nebulas in the night sky, especially because of Hubble images that have been photographed in this region. And it is NGC 6533. This is known as the Cat's Eye Nebula. And it was, like most of the objects in the NGC catalog, it was cataloged by William Herschel. But for the long period of time he assembled this catalog, it was first discovered by him in 1786. If you go look at this visually, which I have done at very sizable optics, it is a noticeably blue hue. It's very distinct blue. But it is a very, very small target. For those who have looked at the Ring Nebula visually, the core itself, which you can see in this right image, this bright blue center is actually smaller than the interior of the Ring Nebula, which makes sense because they're both planetary nebulas, so giving you a sense of scale of the image here on the right. So you will generally need a large aperture or high magnification to go and make meaningful information out of this object. It is it has an apparent magnitude of about 9.8, so it is somewhat bright for objects that we can go see. But overall, it is about 20 arc seconds diameter just for that center portion of that bright center portion of the core. But it does have a very large diffuse outer shell because the star, being a planetary nebula, has ejected all of its outer layers, which form this large diffuse planetary nebula shell around it, which is very much a photographic only target. You won't make much sense of the bright, fluffy outing of this object visually. But what's interesting for a planetary nebula is that instead of being a white dwarf at the center, the central star is actually classified as a Wolf-Rayet star, which is interesting, a little bit interesting because normally I wasn't used to that. Another example here of this object being on 8-inch Smith-Cassegrain with a 10 mm eyepiece. So you are looking at essentially a very bluish star when you go hunting for this object in the night sky. Again, you won't see this diffuse outer shell around this region. Visually, it's very much a photographic target as I for this shell region. And then our last object of the night is NGC 5907. This is a edge-on spiral galaxy called the Splinter Galaxy, and it was cataloged by William Herschel in 1788. It has a visual magnitude of 11.1. It is actually one of the better objects to go look at. I love going to look at this object because it's a very distinct galaxy in the night sky from its edge-on angle that we see. It is also very large for galaxies with an apparent size of about 12.7 arc minutes. So there's generally something that lets you know that you found it rather than hunting very small diffuse blobs. And it has the distinction of being part of a galaxy group that includes Messier 102 that we saw before. So it is part of a, not quite sure if it's a gravitationally bound group or just a visual proximity from our perspective to make a galaxy group for this. It was kind of nebulous on that. But this galaxy is relatively close. It is about 46 billion light years away for galaxies and is almost twice the size of the Milky Way, coming in at 173,000 light years in diameter. So almost the size of Andromeda, I believe. And going back to our simulation of an 8-inch Schmidt-Cassegrain, looking at this with a 10 mm eyepiece, you can see that it takes up pretty much the whole field of view. So definitely useful for if you're taking in, give you some wiggle room here to go bump up to lower magnification eyepieces. Probably a 20 mm would also give you a fairly good view, depending on what your true field of view and apparent field of view are for your eyepieces. Questions or comments on Draco before we move on?
Just a quick question about you mentioned ancient Egypt a couple of times. Um, I'm going to guess prior to Alexander the Great and Ptolemy and so on, the ancient Egyptians probably had their own constellations and so on. Um, so that makes me curious about when did the ancient Egyptians kind of become aware of Greek mythology and
So it wasn't that they became aware of Greek mythology. Basically, what the Egyptians associated this portion of the night sky because it never set for them. It was associated with the presence of the underworld, which is why they aligned the pyramids to it because of these assumption like, hey, it never sets, so it's a beckoning way of saying, hey, this is an immortal portion of the sky, and why they used it for alignments in in their in their tombs and monolith infrastructure. So it wasn't it's this region itself didn't have a constellation as we would today think of it to the Egyptians.
gotcha, cool.
Okay. No other questions other than some like comments. So, Doug, uh, I will let you take over whenever you're ready.
Okay. So tonight I'm talking about stellar navigation, but also as part of that, I how does your telescope know where it is? You know, that kind of thing. How do the go-to systems work and so forth? All right. So before I actually start sharing the presentation, I've got something here in a box. This is called a sextant. The box, okay. You go on board any ship, even today, and most ships, like cruise ships and so forth, they have their GPS systems and they have an assortment of other electronic navigation systems, but they all have these. Every officer on a cruise ship has his own sextant. Guarantee you that. In fact, I know that because I've been on a number of cruises over the years. I've been on over 30, and I've talked with the officers. They all have their own sextants. And even though they've got their GPS systems and everything on board their ship, every noon, every day at noon, you can see them out taking noon sights, usually two or three, taking their sun sights. And every night, at some point during the evening, I'll see two or three of these officers out taking their stellar sights. I don't know whether it's to double check that their GPS isn't lying to them or what, but they do it anyway. Well, I used to live on the East Coast and did a lot of sailing when I was on the East Coast, and I was very curious about uh, being an amateur astronomer. I got curious in navigation. So I got myself a sextant. This is actually a very good one. Now, one thing you might notice, this is not brass. It's not metal. This is a plastic. It's not a normal plastic, but it's plastic. You've probably a lot of movies you've seen sextants and they're all brass and metal and everything like that. Yes, that's what they were made of 100 years ago. That's not what they make them out of today because brass and other metals expand and contract with temperature and also corrode with salt air and so forth. So this is a special plastic that has a very low coefficient of expansion, so it does not, temperature has almost no effect on it, and it's corrosion resistant from salt water and so forth. But it's a relatively simple device to use, actually. You look through the telescope here, pardon me, and there are a number of mirrors that reflect the light from the sky down to this mirror here, which goes into which reflects the light into the little telescope. But that mirror, I don't know if you can see it, the sky here, it's only half mirrored. It's also half transparent. So what you do is you adjust the position of the mirrors to bring a star down to where it's in this mirror and it lines up with the horizon, which you can see through this transparent part over here. You look at it and you point it at the horizon and then you adjust this up and down until you get the star right on the horizon. And then you read the numbers. It's got a scale here. You read it off and there's a vernier knob here, which gives you very fine adjustment. And you can get the elevation of that star above the horizon very precisely, down to just a few seconds of arc. Okay, it really works well. I tested this sextant personally many times when I was sailing just for fun, because we certainly didn't need it. I also took it to beaches on the East Coast where I had a clear horizon of the ocean and sat there and tested it on beaches and checked it out. And with this sextant, I could get my location to within 100 yards. So that's not bad. Okay, so that's the device that's commonly used. All right, let's share my PowerPoint. Okay. Oops. So like I said, the stellar navigation, or how does my telescope know where it is? All right, so how does it, using a sextant to measure a stellar elevation, how does it get me a location? All right, so this is the Earth, and there's some star located at infinity, okay? And all of the rays of light coming from that star, because the star is infinity, they're basically all parallel, okay? So there's only one point on the Earth where the star is directly overhead, okay? There's actually a name for that point. It's called the nadir. I don't know why. But so there's one point on the Earth at any given time where the star is directly overhead. And as the Earth rotates underneath the star, of course, that point, if you were to draw that point, it would form a circle all the way around the Earth at the same latitude, if you can think about that. Okay. But for any given time, for any given point on the clock, that star is directly overhead at only one place on the Earth. Okay. So keep that in mind. Now, if I'm not at that point, okay, then those rays of light are not coming from directly overhead. They're going to be at some elevation angle that's less than 90 degrees, okay? And that's what I use my sextant for, is I can measure that angle, okay, for a star, all right? Now, as it turns out, if in this case we picked some star that's directly overhead some point in the Caribbean, but there's actually a whole circle of points around that star, if you like, where the star has the same elevation, okay? If you think about that, okay? Anywhere on that circle, I'm the same distance from the point directly underneath the star. The star will have the same elevation above the horizon, okay? Anywhere on that circle, okay? So if I measure the elevation of the star, okay, I know that I'm on a circle. Somewhere on the Earth, I'm on this circle that's the same distance from the point directly underneath the star. Okay, there's a whole circle of points. Okay, all right, so that's one star. Well, if I look at a second star, oops, if I look at a second star, I'll get a second circle. Okay, around the point that's directly underneath the second star. Well, the two circles, they intersect each other at 2 points. So in stellar navigation, if you're using a sextant, you have to look at 3 stars. Because when you put a third star on there, the third circle will tell you which of the 2 points is the one where you're sitting. Okay? So there's only going to be one point on the Earth where those 3 circles intersect. And that's where I'm located. So that's what you're doing. That's the problem you're solving when you're doing stellar navigation. You look at 3 stars and you write all the information down from your sextant. And this is the problem, the mathematical problem you like that you're solving, is you got to find the intersection of those 3 circles. Okay? So that seems like a simple problem. Now, of course, it's not. Okay? One thing that you can determine right away, I can very easily, I'm going to back up just a little bit here. One thing I can do is for any star in the sky, if you tell me the universal time, okay, and you give me the right ascension and declination of a star, I can very easily compute where that nadir, the point directly underneath the star, where that point is located on the Earth. That's a relatively straightforward computation. And the elevation if I measure the elevation of the star, I can very quickly determine how far away I am from that point, that nadir point, okay? Because the definition of a nautical mile, okay, is the nautical mile is equivalent to 1 minute of arc in latitude, okay? Or 1 minute of arc measured along the Earth's surface in any direction. So, for example, if I measure a star and the star has an elevation of 75 degrees above the horizon, okay, that means that it's 15 degrees away from being directly overhead, okay? 15 degrees times 60 minutes means it's 900 minutes of arc away from being overhead. Well, that means that I'm located on a circle that is 900 nautical miles from the point directly underneath the star. So that part of the computation was not hard, okay? Um, but of course, there's lots of things that you have to take into account when you're doing stellar navigation. One, you're probably not at sea level. When you're on a ship, you're a good 50 feet or more above sea level. Two, the atmosphere refracts the light in a way that's very predictable, but it affects what you see. The Earth is not a perfect sphere. It's an oblate ellipsoid, and there's other things that you need to take into effect. For example, the thing about not at sea level. Well, if I was right at sea level, okay, like my stick figure there, then the horizon is exactly 90 degrees from the line that goes directly up to my star, directly overhead. But if I'm on a ship, okay, like the figure on the right, my horizon is not 90 degrees anymore. It's actually greater than 90 degrees away from directly overhead. Okay. So that's a correction factor that you put into the math. You have to correct for your altitude, you might say. Um, the tests I did on the beach, I was right at sea level, so I didn't have to worry about that. But when I was out on the cruise ship, I actually did take my sextant on a couple of cruises and did some fun stuff. I had to do the correction for being like 100 feet above sea level. And it does make a difference. And then, of course, there's atmospheric refraction. If the star is directly overhead, the atmospheric refraction is basically negligible. But as the star gets lower and lower and closer to the horizon, you can see how the atmosphere bends the starlight um, like a lens. Okay, and therefore, like if the star is very close to the horizon, like star C on the bottom there, when I look at it with my sextant, I'm actually going to see it at the position C prime. Okay, because the light is being bent by the atmosphere. So again, that's another correction factor that I have to take into account in my mathematics. Okay, and then of course, like I said, the Earth is not a sphere. It's an oblate ellipsoid. And the Earth model that's most commonly used by GPS and most navigation systems is what's called WGS 84. I think that stands for World Geodetic Survey, 84 being the year 1984 when it was done. It's periodically updated. The last time it was updated was last year, actually. And your GPS system and everything takes that into account. And it's also taken into account when you do the solutions, if you use a sextant to do the measurements, it's built into the solution system that you use to solve the equations. So here's the thing. In addition to finding a sextant on every ship, and every officer on board a cruise ship has their own sextant, they also have one of these. This is what's called the Nautical Almanac. It is published every year by both the Naval Observatory in Washington, D.C., and the United Kingdom Hydrographic Office. Used to be about 20 years ago, this was actually published by in addition to the Naval Observatory, it used to be published by the Royal Greenwich Observatory, but they've set up a hydrographic office now that publishes this book. This book is just chock full of tables. Every page is a table. There's hundreds of them. And most of these tables are what's called site reduction tables. And essentially what these tables are lookup tables. Okay, you go into the table using the data you got from your sextant and you look something up, and then you go to the next table and you look something up, and you go through these tables. And what these tables are essentially doing is they're solving the math equations for you. The tables have the Earth model built in. The tables have the refraction tables built in. The tables have um, the altitude table is built into all of these site reduction tables, and you just walk your way through the different tables and steps, and you end up with a solution. Okay, so you don't have to sit down and solve the math equations, which are terrible. We're talking spherical trigonometry and a bunch of other stuff. These site tables, these site reduction tables, allow you to just go through, step through the tables, and you can end up getting a solution in like 5 minutes instead of taking hours. They also have tables in here that gives you sun site information, like what time of day in universal time does the sun reach the highest point in the sky? Or in other words, when is apparent noon for every day of the year. Okay. And also the same thing for like the 50 brightest stars. It tells you what time of day that star reaches its highest point in the sky. Okay. And also does that for all the planets. So very useful book. It would be very difficult to do the site reductions equations. I've looked at them and it's like I don't really want to do them. It would be very difficult to do if you didn't have these books, but everyone who has a sextant has one of these. Um, all right, so this is how you do navigation using a sextant. Now, the next step I always ask myself is, okay, so how does this relate to amateur astronomy? I was very curious. Well, okay, let's go back. Most go-to systems, you do what's called a two-star alignment. Okay. Um, Essentially, you're doing the same thing. You're using your telescope as the sextant, okay, if it's an as-L mount, okay, and you're measuring the elevation of the star with your telescope, essentially, and you're putting in a time, okay, the telescope knows what time it is if it's been set properly. So you got a time and an elevation for two stars, okay, but not three. I think some go-to systems you can actually do a three-star alignment, but most of them you don't have to. You can do a two-star alignment. So you may say, well, okay, I'm doing a two-star alignment. How do I know which one of those 2 points where the two circles intersect? How does the telescope know which one of those 2 points to use for its location? Well, because you've got one additional piece of information your telescope does that you didn't have when you were using your sextant. You've got an azimuth, okay? You've got an azimuth um, location for both of the stars. I guess it would really only need one, but you've got the azimuth on both of the stars that you picked for your alignment. And using that, it can figure out which one of the two intersecting points there is the one where the telescope is located. So now it's got all the same information that I got from my sextant. It knows which point to use, and it's going to go through and it's going to solve those equations. That's all built into the computer system. It knows the model, the WGS84 model, and it's going to go through and it's going to solve all the math and everything that I did with the nautical almanac. And that's how the two-star alignment works, essentially. So that part's easy. So that's how the two-star alignment system works. Now, I was also curious. I always wondered about this. How does GPS work? I never really understood how the GPS works. I know that it's getting time signals from satellites and it's using that to somehow figure out where I am on the Earth and also to figure out what time it is at my location. And I never truly understood how that works. So I said, okay, while I'm going down this avenue of stellar navigation, let's see if I can figure this out. Okay. So I'm going to avoid using math here. There's going to be a lot of complicated math in doing the GPS, but as it turns out, the concept is actually very simple and doesn't require math to understand the concept. So first of all, you've got a number of GPS satellites in orbit. There are currently 31 of them. The orbits are arranged in such a way that no matter where you are on your service, you're going to be able to see several of the satellites. Okay. And that picture down in the bottom right, there you can see the orbits are all kind of, they're covering the whole Earth. They're not just around there. Now, as it turns out, each GPS satellite has an atomic clock. All the satellites are synchronized with each other. Um, they all, at any given time, they will all have the same, their clocks will all read the same. They're synchronized. This is done by, there are a number of ground stations around the world, and every time one of these satellites go over the ground station, there's a sync signal that it looks at that's being transmitted by the ground station. And that allows the satellite to, quote, correct its clock. So these satellites are all in synchronization. Okay. Now, the satellites are very smart. They have to take into account relativity and all kinds of other things. They have to adjust their clock for relativity because they're going fast. Um, Not real fast, but I mean, they're going fast enough to where there is a time dilation to the clock. So they have to adjust their clocks for that. Also, they're farther out from the center of gravity of the Earth. So there's also a relativity effect for that. Um, they have to adjust their clocks for that, and so on. The satellite knows its position in space very precisely. And again, this is done by, it knows, it keeps in touch with the ground stations and it gets the sync signals from the ground station. And Newton's laws work very well. And so the satellite is constantly calculating where it is based on Newton's laws and relativity. It also knows how fast it's going, so it has to make corrections for that. All right, so that's what the satellites are doing. Now,
Real
what the
quick, Doug,
satellites,
before you move on.
go ahead.
Another interesting thing about the GPS clocks is that, like how on the ground we have different time zones for different time for different locations, like we
Yes,
have Phoenix time zone, Eastern time zone, etc.
sure,
The GPS time clock is also its own discrete time zone.
correct. Doesn't care about what the time is on the
Yeah,
Earth.
so
I don't know whether, yeah, I should have looked this up. I don't know whether they're all set at like universal time or something, but they're
they
all,
notice as in they don't use universal time at all. They actually have their
oh,
time
just
is their own distinct time.
oh, okay. All
It's
right.
actually like GP some. It's actually its own distinct time code.
Okay.
It's
That
not part
doesn't
of the
matter.
UTC
That
system.
turns out it doesn't matter. As long as they're all synchronized, that's all that matters. Okay, so now each satellite is transmitting its time and a position. I don't know how often they transmit their signal, but they're constantly transmitting position and time, position and time, position and time. And this is what you're picking up with your GPS receiver on the ground. Okay? Now, for the sake of simplicity, like I said, we're going to do this as simple as possible. I've got a GPS receiver on the ground. The red star is my GPS receiver. And I've got three satellites. I'm picking up three satellites, S1, S2, S3, and they're at different distances. They're different distances away from the red star. Now that means that the three signals that I get at any particular time at my red star, I'm going to get position and time signals from all three satellites, but they're not going to read the same because it's going to take longer. The signal from S3 is going to take longer to get to me than the signal from S2. So the signal from S3 is not going to read the same time as the signal from S2. The signal from S3 that I pick up is actually going to be an earlier time than the one from S2 because the satellite's farther away. It takes longer for that signal to get to me. So that's going to actually be an earlier time than S2 and so on. So the signals I get from the three satellites are all different. They're going to be different times. Okay. So I've got three signals, and it turns T2, the signal from S2, is going to be the latest time. That's going to be greater than the T1, which is the second farthest satellite, and that's going to be greater than the signal from satellite 3. Okay. So I can, so I know that. Um, I don't know the distances to the satellites. Okay. But I do know this. The distance for the satellites is basically the travel time that it takes the signal to cover that distance divided by the speed of light, the propagation time. Okay. And so I can write some very simple equations like the distance from satellite one is the difference between the clocks, okay, divided by C and so on. Okay. And I can write those same equations out for all three satellites. These are very simple. Okay. The difference between T0, that's the current time at my location, minus the time at T1, the satellite, first satellite, I can write as my current position minus the position for satellite one divided by C. Okay, and I can do that for all three of them. Now, these are very simple. Obviously, there's a lot more to it than that. But what I end up with, okay, is the three equations, okay, like that. Now, as it turns out, for GPS, to get a proper solution from GPS, you need 4 satellites. You can't do it with 3. And the reason being that you're solving for 4 unknowns. You're solving for uh, one time, the current time at my location, okay, T0 in those equations, and I'm solving for P0, which is my current position or in the ground. But P0 is a three-dimensional coordinate in space, X, Y, and Z, if you like. Okay. Everything else in those three equations is no. I know T1, I know T2, I know T3. Those were the times I got from the satellites. I know P1, P2, and P3. Those were the positions I got from the satellites. So I'm solving for the unknowns, T0 and P0. And like I said, P0 is a three-dimensional coordinate. So I've got 4 unknowns. I can't do it with 3 equations, okay? But I can do it with 4 equations. That's why you need 4 satellites to get a proper GPS solution. Because then you end up with 4 equations and 4 unknowns. And you crank through the math and out pops the solution. So that's how GPS works. Okay? Surprisingly simple idea. And I think that's my last slide. Yes, it is. Like I said, the receiver has to take into account the atmospheric refraction and the Earth model, time delays from the electronics, which they know what that is. Um, the GPS satellites, they're doing all the stuff that for relativity and everything else, but surprisingly enough, what you're doing with what the GPS receiver and satellites are doing is very similar to what you do with a frigging sextant. You're solving a lot of the same problems. Okay, questions?
Yeah, Doug, first of all, a year or so ago, I looked up nadir and zenith. My recollection is they're both derived from Arabic words,
Yeah,
misspelled over the many years, of course. It was something else, but and basically my recollection is zenith means straight up and nadir means the opposite of straight up.
right.
Uh,
Nadir is straight down, and so the point directly underneath the star, like if the point directly underneath Vega on the surface of the Earth, you'd actually refer to that as Vega nadir.
okay, makes sense. So to know where Vega nadir is, I need to know what time it is.
Universal time would be
Uh,
best.
right. And of course, I need to know.
It's quarterly.
star ephemeris, I
So if
guess.
I, yeah, well, no, date and time, okay, is all I would need, date and universal time, okay, and then right ascension and declination for the star. And I can figure out where the nadir is for any universal time on any day. It's actually a straightforward computation. I mean, okay,
Okay.
for example, I'll give you a perfect example. Um, Suppose Vega is directly overhead, or let's just say, for the sake of argument, I know this is not true, but Vega has a right ascension of 0 hours and a declination of 60 degrees. Okay. So I already know that all the nadirs for Vega are going to lie on a circle at 60 degrees latitude. The nadirs are always going to be on that one circle on the surface of the Earth.
Of course.
Okay, now I say the right ascension is 0 hours, just for the fun of it. Okay, so and then let's just say that I know from the definition of 0 hours right ascension that that point is directly overhead Greenwich Observatory at noon on March 21st. Well, now I can figure out, give me a day of the year, and I can figure out where that star is
Okay.
at that particular time because I can figure out how much has moved in one direction or 6 months later at noon, the nadir is going to be 180 degrees away. All right. You
Right.
see, the calculation is actually fairly straightforward.
Okay. Well, then I don't need to ask you my other questions, which was going to be, um, do you need a table for that information, like in the almanac? And it sounds like you
Well,
don't, because
well,
if you know the right ascension declination, you're good, and the time.
the table is helpful because what those tables give you for a lot of that information, and yes, you could figure this stuff out by hand. But as I said, the math gets very complex very quickly because you're taking into account, the atmosphere and the altitude above sea level and all that stuff gets built into the equations over time. So the lookup tables are nice because you just walk, they're built as a series of steps. You go into table one, look something up. Then you take what you got from table one and you go on to table two and look something up. And you walk through these tables like that. You could do it all by hand, yes. But also, even for the example I gave you, while I can calculate where I believe the star's nadir is going to be at any time and date, okay, if I know its right ascension and declination, you've got things like the Earth is not rotating at a constant rate. It changes during the year.
Mhm.
So while I think the star will be 180 degrees away 6 months later, it might be 181. Okay. Yeah,
Yeah.
because the Earth is not perfect and, you know, so the tables are nice because they take care of all that kind of stuff. So it's useful to look them up sometimes.
So where I was going to go, depending on that answer was, um, so it sounds like you could use any star
Yes.
that you can see. What I was going to ask was, do they pick specific ones, like Vega or whatever? And it sounds
No,
like you can use any.
you can use any star that you can see with your sextant. Okay. Now, what I found when I used this guy was anything dimmer than about fourth magnitude didn't show up too good with this. I had a hard time seeing stars below fourth magnitude in the sextant. It's just it doesn't magnify much. This little telescope here. Let me stop sharing. Um, this little telescope right here um, doesn't do much in terms of magnification. It's only about 3 power, and with the mirrors and everything in the lenses, they're about fourth magnitude is about far down I can get. That's a lot of stars. I mean, the Nautical Almanac has the 50 brightest stars in tables so that you know exactly where they are at any given time of the day and so forth. And they always say you should use the brightest stars you can find is what they always suggest. Okay. But they do suggest also that, you pick three stars one over here, one over here, and one over there. A good wide spread. So you get your three circles spread out. You don't want all your three circles in one place because then there's a certain amount of uncertainty built into the thing. So, but yeah, they do recommend go for the bright stars if you can find them.
Much like the same reason why you would use bright stars on your own scope, because you're like, I know what those stars are. I don't have to
Yeah,
guess
I
on them.
mean, when you're doing a two-star alignment with your telescope, I mean, you pick Vega, you pick Arcturus, you're picking bright stars. Okay, not for the same reason, not because the telescope can't see the six magnitude stars, but I mean that's just I think normal instinct.
It just removes ambiguity from like, is this really this star?
Yeah, I mean,
Arcturus
exactly,
is easy as fine.
absolutely.
So thanks, Doug.
Yeah,
Yeah, that was really cool, really interesting, and good explanation too. I was able to follow it real easy.
the concept's easy.
The
The
math isn't.
math isn't.
Makes me kind of wonder what kind of computation power my GPS receiver needs or my cell phone needs.
It's just doing linear
Uh,
algebra, not much.
More
Okay.
than linear algebra. It's doing, like I said, it's doing spherical trigonometry.
Mhm.
Right, but it solves the equations of unknowns with
Yeah,
uh,
it's going through the lookup tables is what it's doing.
yeah. But so with that, I'm gonna go ahead and call that a night since it feels like we're out of questions and stuff like that. So thanks, Doug. And then